Let's continue our earlier theme about the fiber orientation. We derived a set of equations, probability densities and so on, number of fibers, for fiber structures, for planar types of fiber structures. This distribution of directions is very important for a lot of properties. At most, for mechanical properties of fibrous assemblies. I want in this lecture to present one case how is possible to apply our earlier knowledge to the mechanical behavior of fibrous assembly. But I must say, in our lecture, it will be an easiest case. So easy that it is on the border of unreality. Each real structure is much more complicated. So that, but I want to present it to you because it can show how is the style of our work when we must to derive some model for mechanical property of a fibrous assembly with some distribution, significant distribution of fiber direction. Because this methodological sense, I want to present to you this easiest case. On the final sentences, I will in short comment what's possible to do more and go more to the real, means more complicated structure. So that easiest case of mechanical behavior of planar fiber assembly. Let's accept 6 assumptions which make our problem easy. First, our model is planar fiber orientation. It's a planar fiber. Second, each fiber is straight. It means no crimped. Also, cotton fiber have some small crimp. But we assume that each fiber is straight. Then, third, each fiber is clamped by both jaws of tensile machine or braking machine. Yeah? And we neglect the effect of the emergence of jaws. You know, when we have something like non-woven, some web or something so in couple of jaws in braking machine, we must cut this structure by the end of jaws. Yeah? So that some fibers are like this here. We don't want to calculate these fibers. You can imagine that the jaws are very long, yeah, and this age between this value between a couple of jaws is very small. Fourth, because I said easiest model, let's imagine a linear force strain relation, same for each fiber. So between the fiber force Fl and the fiber elongation epsilon L is the relation strand by braking strain times epsilon. This is the constant for fiber times epsilon L, and 0 of course after braking, but we will this next assumption, small deformations, so small that no one fiber will destroyed through our process. And the last of our assumption is that the fibers are deformed mutually independently. We don't calculate the friction, fiber-to-fiber friction in our structure, and so on. Well, first step, let's derive the function of per one fiber, one general fiber between jaws. We have some couple of jaws in a braking machine, and a green fiber, length L, is clamped between these two jaws. Length of the fiber is L. Starting angle, we will need, it's enough to know, non-oriented angle theta is shown on the picture here. Yeah. Vertical axis is our earlier y-axis. Well, so H is gauged after first intuitively after elongation, after jaw displacement, the jaw B is changed the position to the new position B dash. Therefore, the fiber is now this here, length L dash higher than length. So that's L dash. Epsilon we call as a relative jaw displacement, and it is from H length and H dash defined traditionally. Relative jaw displacement. In opposite to them, the strain in fiber work with L lenses. So that is L dash by L minus L by L evident. Yeah. The starting angle theta, for the starting angle theta, it's possible to write that it is cosinus of this is H by L, which is shown from the figure. The final angle theta is the angle after elongation, which is similarly from the picture here, H dash by L dash. And because H dash is H times 1 plus epsilon, and L is L dash is L times 1 plus epsilon L, fiber strain, then we can write that the cosinus theta dash is cosinus theta starting angle times this ratio, 1 plus epsilon by 1 plus epsilon L. You know the Pythagorean theorem, isn't it? It's a very known theorem in whole world. Therefore, we want to use it 2 times. First time from this triangle, from this yellow triangle. And what we obtain from Pythagorean theorem, x square is L square minus h square, isn't it? Well. From the second light green triangle, we obtain x square is L dash square minus h square. Because this length x is same for yellow triangle as well as for light green triangle. Why? Because our jaws are from some metal and not deformable. Now change by this vertical moving of the jaw B. So that it must be valid. This is equal to this expression. It's here. It is here. Now some small rearranging, which of we divide this equation by L so that we obtain this here. Sorry, L square, of course. Yeah, by L square we divide. Using our symbols or our equations known from here, we can write 1 minus cosinus square theta is 1 plus epsilon L square minus h to 1 plus epsilon by L square, so that it is this one. because h by L is a cosinus, yeah? So I have this here. From this equation, this is possible to arrange in this form, trivially. And epsilon L is this here, or epsilon L we obtain or epsilon L is possible to explain using this expression. That's good. It is shown that the strain of fiber is not the same than jaw displacement epsilon, and that it is a function also of angle theta. It's based on the orientation of our fiber segment, our fiber. Well, we said our model will be the easiest as possible. Therefore, let's imagine small deformations, very small deformations. Then epsilon is very small, and then the approximate value, equations are valid. You know that we can construct the different approximate formulas using Taylor series, isn't it? It is known from mathematics. And using such, but exists also some content of different, often used approximation equations. The one say 2 times epsilon plus epsilon square is roughly, for very small epsilon, 2 times epsilon. Because the square is extremely small, then we can neglect it. Square root of 1 plus 2 times epsilon cosinus squared theta, if epsilon is small, if this part is very small, is possible to write approximately as 1 plus 1/2 of this. Yeah. The third is nothing. This 2 is in the moment enough. Then our epsilon L was this here. Using these approximation equations, we obtain that it is this here. This is approximately this, so that epsilon L is epsilon times cosinus squared theta for small deformations. In this easy equation, you can see that the function of angle theta. When we have a fiber with higher angle theta, then cosinus is smaller than 1. Cosinus square is much more smaller than 1, so that the epsilon L is smaller than epsilon. The highest value of strain of fiber is when the fiber is parallel to jaw axis. Here higher is this angle theta, yeah, from the direction of jaw axis. So smaller is fiber elongation. It's a result of this equation. It was something about the fiber strain. Now about fiber forces. We said that the force in fiber follows the linear function, so that the force in fiber Fl is proportional to P by A, fiber strain by fiber breaking strain, times fiber strain, actual fiber strain, epsilon L. Yes. How is the force? I can say vertical force. This force Fl have 2 components, and we measure in our braking machine. We measure this vertical force. Yeah, it can be the special speech about this horizontal force. It had something together with moment, frictional moment in yarn, but it is in each structure, especially in yarn, it plays the interesting role. But we spoke about our vertical force in relation to our picture. So that how is the vertical force? No, the force Fl times cosinus of our angle theta dash. From our picture. Using our equations, we obtain this here. Using our equation, we assume small deformation, then epsilon L is given by such equation. After rearranging, we obtain this equation. And because small deformation, we can also write that 1 by 1 plus something small is roughly 1 minus something small. Yeah? Also some approximation formula, known formula. And we can also write that epsilon plus epsilon square times sinus square of angle minus epsilon power epsilon cube times cosinus square and so on is roughly equal to epsilon, because epsilon square is small and epsilon power 3 is much more smaller, isn't it? So we can write it's epsilon. Using this approximation, we can this function rearrange as follows. This is, I think I need to comment this rearranging. It's rearranging on the level of your high school. On the end, you obtain this expression, and because this is approximately epsilon, we obtain that the vertical force is proportional to epsilon, this is imaginable, and for cosinus of angle theta, power to 3. Okay? Now, it was one fiber. We derived the vertical force per one fiber. Yeah? Now, how is the total force on the braking machine by jaw displacement epsilon? Yeah, I said we assume that the vertical axis, the axis of jaws is our earlier y-axis. The distribution of angles theta corresponds to our probability density function u star theta, which we derived in our earlier lecture. Because clamp line of jaw is the same as the section line, evidently. It's not the same, but in the model it is the same. Okay. We derived earlier the number of sectioned fibers per unit length. It was G by T times Kn, where Kn was also this integral. And what was G? G was mass, weight of our planar textile per mass unit. T is fiber fineness, you know, and at most in decitex or something, so isn't it? Yeah? And what is Kn? We discussed a long time in the last lecture. Now we will speak about fibers. In short, I say having the direction theta. What I mean that more precisely, let's imagine the elemental group of fibers which have angles from some value theta to theta plus d theta, some elemental angular class, class interval. So that in this class interval, the relative frequency of fibers is u star theta times, u star theta times differential quantity d theta, so that the number of fibers in this interval per unit length of jaw is what? Total number of fibers per unit length of jaw, it was in our earlier lecture, nu, and times probability density. In earlier lecture, we remember that this is evident and this is valid. Okay. And then the vertical force due these fibers is dr, which is force per one fiber times number of fibers times number of all fibers times relative frequency. All these two members together means number of fibers having angle theta. Yeah? It's number of all fibers per unit length of jaw times the relative frequency of fibers having angle beta. Using these expressions, we know the equation for each of these quantities. We obtain dr in such. Oh, it's not well. Maybe I have here, and yes, I have here one mistake. Sorry, nobody is perfect. It must be no. All bad, all back, all is well. All is, and it is not a new equation. It's the same equation which continued after rearranging. Well, and now how is the total force? Total force is not the force only from the fibers having our angle theta, but for all fibers. So the force per unit length of a jaw, r, must be an integral from dr, isn't it? Over all angles theta. It is unoriented angle, then for theta equals 0 to theta 90 degree, theta pi by 2. I must remember that in theoretical words, every time we work with radians, now with degrees. We can say degree because it's better for our imagination, but we must work with radians. Well, using this, we obtain such equation as a resulting equation for the force which we need, because realize the displacement between jaws equal epsilon. So it based not only to our epsilon, it based also to distribution of orientation of fiber segments in our structure. Oh, it's evident that if G is higher, if mass of per unit area, mass per square meter, for example, is higher, then we have more material and the force will be higher, and so on and so on. It is not too important. Therefore, let's calculate a special case, and then something like it will become some utilization coefficient, which can say utilization of mechanical utilization fibrous material. In opposite to earlier case, in which all fibers in between jaws have each fiber have its own special angle theta. Let's imagine another structure in which all fibers will be parallel to jaw axis. This structure is shown here. All green dotted as well as continual line are fibers here. So let's imagine the situation in which between our jaws, our fibers are parallel to jaw axis. Let's imagine that we take each fiber and we rotate each fiber to the position to be parallel to jaw axis. Yeah? Then we obtain such structure. Same gauge length h, length unit in jaw. The number of fibers in the length unit of jaw in this case is evidently maximum. Yeah. Mass area is mass by mass area in this rectangle 1 times h is, which G is mass here of this fibers times area 1 times h. But the mass, what is the mass? The mass is T times nu max times h. Nu max is number of fibers here in length unit of jaw. Each fiber have length h, so that L times nu max, its total length of fibers in our rectangle, 1 times h. Total length, and nu times and from the definition of fineness, we can write that the mass is T times nu max times h. Using it, we obtain this here, T times nu max, so that number of fibers nu max is mass mass per areal unit by fiber fineness. Okay? Well, this is the number of such fibers. How is the force? The strain of fiber, generally was epsilon L, is now equal epsilon, because all fibers are parallel. It's equal to jaw displacement, epsilon. So that I can write that one fiber, it's very easy, on one fiber is the force F max, which is our linear equation for strain relation by fiber, but times epsilon. Epsilon L is no needed now because epsilon L is equal to epsilon. So per one fiber we obtain the force F max, and then the total vertical force per unit length of the jaw clamp line. What is it? It's number of fibers times force per one fiber. Using it, we obtain this very easy expression. Okay? We have two forces. One is for our, let's imagine, a real structure having the orientation, and second is for the structure from same fibers with same mass, areal mass, yeah, but oriented parallel to jaw axis. One is R, second is R max. We can construct the ratio R by R max. It can say us how is the mechanical utilization of fibers during the effect of fiber orientation, isn't it? Here we have a real include the effect of orientation, and in denominator it is without the effect of the of orientation. And using this, you can see that this blue part before integral here is the same that R max, so that we can write that the mechanical utilization in our easiest case, which we solve, is given by integral from theta from 0 to pi by 2 from cosinus power to 4. Very strong, very hard effect of cosinus times u theta d theta. So you can see that this effect, this utilization is can be can be sometimes very small. It's going from 0 to 1, isn't it? But sometimes it can be very small. When we use on the place of u theta, our u theta from our model, with spikes and the imaginary flexible belt and so on, so that you use this u theta according this expression, we can calculate it, and you obtain based on c value following curves. This is alpha angle from minus 90 degree through 0 to plus 20. Means, let's imagine something like web, or from web some fleece, or I don't know what, maybe also sliver. Today we discussed with Professor Richtiak about the possibility to apply such equations to sliver and so on. Let's imagine some structure, and now when it is planar structure, you can take your experimental part to braking machine in different angles. You can jog it to longitudinal direction or right or left, in small angle, higher angle, much more higher angle. Yeah, clamp it in the results was different based on this angle alpha. Why? Because the angle alpha is here. Angle alpha is here. Yeah, we are integrating over theta, but angle stay be here as a constant, as a parameter of orientation of our web, for example, in relation to jaw axis. So we obtain these curves based for different value of c. For example, evidently for c equal 1, what it means? Isotropic structure. You can rotate the structure how you want. The utilization will be permanently same, constant. When you use web, then maybe you obtain c, you will work with c equal 2 roughly. We show that the typical web have c roughly near to 2. Then you will work with this function. The value here by the utilization value is roughly 2 times higher than here. The utilization value by longitudinal direction is roughly 2 times higher than by cross direction. Yeah? It is often used in textile industry. The people don't have time and instruments for deeper study of similar problems. But they have braking machines, and they have the products which they produce. In a non-woven, often used the strand in longitudinal direction and strand in cross direction, and ratio constructed from these two values. Yeah, longitudinal to cross direction. It can show. It is the very easy, the practical way how to characterize the how to say it intuitively only, the degree of orientation. Yeah, the intensity of orientation which was used. So you can see it on this picture how it is by c equal 2 and so on and so on. Yeah. So fiber orientation have significant role or play significant role to mechanical properties of fibrous assemblies, different fibrous assemblies. Now to our easiest case and reality, some last words. Normal way we often work with staple fibers, so that some of fibers are not clumped in both jaws. So you need to formulate this problem mathematically and reduce the number of fibers in jaw only to fibers which are clumped by both jaws. Second, on the end of jaws, some fibers on the end of jaws, here on the other side too, some fibers are cutted. Therefore, although they are not in both jaws, because was sectioned by your preparation of your experimental material. It's possible to calculate how many fibers and so on and give it in our model 2. It's the second influence. Third, you said fibers are straight. No, fibers are not straight. Usually fibers have some crimping. Maybe very important, maybe small, but every time something it is. Then the fiber for strain curve is modified through this crimping, Also in parallel fiber bundle, about which we will speak later, when the fibers have some distribution of such crimp, then the mechanical effects are significant. Dr. Das helped me prepare a special publication to this problem. Well, it is, I don't know, third influence which we don't to use. Linear force strain relation. It is only an easiest theoretical example, but in reality the force strain curve for fiber is fiber to fiber different, so that you need to use similar way, but use inside of our equations nonlinear curve of force strain relation related to especially your fibers. Yeah. Well, this all is possible, maybe good, maybe not so good, but to formulate using some theoretical tools and make some modified model which is much more complicated, but nearer to the reality. The last assumption, the fibers are deformed mutually. It is very difficult to give out, because to this time, I personally don't know another good model how to input to our model the friction phenomenon between fibers. I know only that the traditional equations, like a Coulomb equation, friction force is proportional to normal force, or the other equations which based on the Coulomb idea, means Euler friction and so on, are not enough well for textile structures. But what's well from point of view of friction, it's quite open question which is waiting for you maybe. Some of you will be researchers, will be scientists in future, and then you must solve the problems which we, old generation, didn't solve. Well, I think this is for this team. All, thank you very much for your attention. Be happy and goodbye.